Okay, we're going to use the next example to illustrate what's going to happen in the next section. I'd like to integrate 1 over 4 plus x squared dx. I have no technique up to this point I can use other than the trig substitution. Notice it's of the form a squared plus x squared. So I'm going to start again by changing the integral using that particular trigonometric substitution. So we're going to use x equals a tangent theta, and our a is 2. So x is 2 tangent theta. Take the derivative, dx is 2 secant squared theta d theta. And again, remember what we do is we substitute in. So in for x, we put 2 tangent theta, and in for dx, we put 2 secant squared theta d theta. Simplify the resulting substitution, so I'm going to square the 2 tan theta, which will give me 4 plus 4 tangent squared theta, and then multiplied by 2 secant squared theta d theta. Again, like I did before, I'm going to factor out a 4. This time it's not in a radical, but I'm still going to factor it out and cancel. Notice since it wasn't in the radical, we're still going to have something left when we cancel. Right? 2 goes into 4 twice. Now, 1 plus tangent squared theta. Hey, we used that before. That's secant squared. Again, it's not in the radical, so I can't take the square root. I will just have secant squared theta. You'll also notice that I brought that 2 out in front, and since it was in the denominator, it came out as 1/2. So now I have 1 over secant squared theta multiplied by secant squared theta d theta in the integral, and a 1/2 out in front. I'm sure at this point you know, hey, cancel secant squared theta, and we're just left with 1/2 of 1 d theta that we're integrating. So if I integrate the result, again, this is a theta integral, so the antiderivative of 1 is theta. So I have a 1/2 theta plus c. And now we're all done except we need to go back to x's. This is the one where we don't really need the right triangle because we don't have a trigonometric function. So I knew x was 2 tan theta, so tan theta is x over 2. And I'm going to take the arctan or inverse tan of each side. Right? So if I do inverse tan of tan theta, that's going to equal inverse tan of x over 2. Inverse tan and tan cancel. So I get theta is inverse tan of x over 2, or theta is arctan x over 2. And your book will be using the arctan notation for these problems. So a 1/2 theta plus c is a 1/2 arctan x over 2 plus c. So I want to generalize this before we go farther. And here's the rule we're going to be using. In general, if we have a constant over a squared plus x squared, no square root, has to look very much like this or could be written in this form, the antiderivative of that will be k over a arctan x over a plus c. So if we were to look at our example, which was the antiderivative of 1 over 4 plus x squared dx, if I just applied the rule, our k is 1. So we'd actually have 1 over, our a is 2, remember, arctan x over our a, which is 2, plus c. So we don't need all that work. All we just need to do is go right to the formula. And that's what we're going to be doing in the next section. We're going to be looking at problems like that, or that can be written like that, in order to do some integration.